Now we want to apply the concepts of stress, strain, and elastic moduli to a spring. So let's pretend that the spring is nothing more than a piece of metal that originally has a length L sub 0. Then we're going to apply a force to it, and then it's going to stretch this much, delta L. So the stress is going to be the force that you apply divided by the area of this piece of metal here. And then the strain is going to be how much does it stretch divided by what was its original length. And then the elastic moduli is going to be the ratio of the stress to the strain. So it's going to be force divided by area divided by change in length divided by L sub 0. And now what I did was I rearranged it for F. So I took all of this material and I put it on this side of the equation so that I get the force that I apply is going to be equal to the elastic modulus, so EM, times the area, and then divided by the original length, and then times the change in the length. And then what we can do is lump all of this together. So all of that is another constant, which we're going to call the spring constant. So C subspring, the spring constant. So this is what I would want you to understand if you were taking a course, that the formula for the force on a spring is going to depend on what is the spring made of, so that's going to be incorporated into the spring constant, and then how far does it stretch, so that's going to be delta L. So here's a sample question. A 50-gram object is hung from a spring, and the spring has a spring constant of 100 newtons per meter. How far will the spring stretch? So we're going to write down what we're given and what we're looking for. Remember, grams is not the official metric unit for mass. It's the kilogram. So 50 grams becomes 0.050 kilograms. Then you got your spring constant. We want to know how far is it going to stretch. And so the force that is going to be stretching it is going to be the force of gravity. So the force of gravity is pulling the object down. And then this is balanced by the spring force, which is trying to make the spring smaller. So we're going to set the two forces equal to each other. The force of gravity, which is mg, where g is the acceleration due to gravity, 9.8 meters per second squared. So we're going to set that equal to the spring force, which is minus the spring constant and then how far it stretches. And then we plug all of our numbers into that, and it turns out to be 0.049 meters, which in terms of centimeters would be 4.9 centimeters. Here's another sample question. Two springs each have the same weight hung from them. One of the springs has a small spring constant, while the other one has a large spring constant. Which spring is going to stretch further? So we're going to write equation 10.5, the formula for the spring force. We're going to write it twice. So we're going to write the formula for the spring force for the one that has the small spring constant and then the one that has the large spring constant. Well, you should also notice that in algebra that 4 times 1 is the same thing as 1 times 4. So if one number gets small, the other number has to get big in order to compensate. So since they have the same force acting on them, then that means that the one that has the small spring constant is going to be the one that's going to stretch the furthest. So think of like a rubber band versus a shock absorber. So that if you apply a force to a shock absorber, it doesn't really stretch. But if you apply it to that rubber band, it really does. So that's telling us that the shock absorber has a very, very large spring constant. All right, we're going to take a break, and when we come back, we're going to talk about what do materials really do when you apply a stress to them.